Welcome to Biomaterials. What are we going to talk about today? Well, today we're going to talk about what happens if you load and unload the stress or the force on some material multiple times. What happens if you load and unload multiple times? And we're going to break apart this lecture into a few parts. The two main parts, well, the first part we're going to talk about is what's called strain hardening. It has a few other names: cold work, work hardening, and there are a few others. But this phenomenon is basically a phenomenon in which if you strain a material past its yield point, you can actually permanently alter the stress strain curve. So we'll basically talk about when strain hardening happens, right? Under what circumstances does strain hardening occur within a material? We'll talk about permanent changes to the stress strain curve that are sort of that occur with strain hardening. We'll talk about the effect on material properties. Right, some important material properties, for example, the yield stress, toughness, and the strain to fracture, and maybe a few others. That sort of are not so subtle effects of the permanent changes that occur to the stress strain curve, right? Obviously, if the stress strain curve changes, then a lot of these things change. We'll sort of discuss those implications. And with these changes on the material properties that accompany strain hardening, we'll talk about implications for design. And then we'll talk about this sort of more specific phenomenon that is related to strain hardening, which is called necking, which is something that can occur when you're trying to do materials testing. Then we'll sort of move on to the second phase of today's topic, which is what happens when you unload and load multiple times, which is this phenomenon of fatigue. So, if we're not too tired by the time we get there, we'll talk about fatigue, which is basically if you load and unload something, even if you keep it below the yield stress, even if I stress something not enough to cause permanent deformation initially, it turns out that materials can still fail even if you keep them below their yield stress, if you load them and unload them multiple times. So we'll talk about this idea of stress cycles. And then we'll plot what's called an SN curve, which is basically a safe limit versus the number of cycles that we need that thing to sort of survive before we can tolerate failure, versus the number of cycles before failure. And so that's the nature of the SN curve. And of course, this has implications for design. And then one key feature of the SN curve for many materials, not all materials, but lots of materials, is what's called the endurance limit. And it turns out that this is basically a stress level, a safe stress level, where n cycles can be, we can actually sort of support hypothetically an infinite number of stress cycles without failure occurring. And endurance limits exist for some materials, for example steel. Turns out it doesn't exist for other materials, for example aluminum, and we'll talk about some design implications for that. So let's hop back to the first topic that we were going to talk about, which is basically strain hardening, also sometimes called cold work or work hardening. So when we're thinking about material properties, we talked about the stress strain curve. And today we're going to talk about how the stress strain curve relates to strain hardening. So let's get started with let's get started sketching out a stress strain curve. So we put stress on the y-axis, strain on the x-axis, and this phenomenon of strain hardening is something that predominantly occurs in metals. So that's basically what I'm going to restrict our discussion to today, right? So a lot of medical devices, implants, things like that. You know, metals have phenomenal mechanical properties in terms of high stiffness and high strength, and all those things. So basically, we use metals for so many things that, you know, it's worth talking about them. Sometimes strain hardening can occur in other materials, but we're going to focus on metals today. So if we plot stress versus strain, if we plot such a curve for a ductile metal, you know, we have this linear region right here, and then after the yield stress right here, we have the sort of plastic region, right? So we have the elastic region right here, we have the plastic region right here. There's the yield stress that corresponds to this point where it sort of simultaneously deviates from linear behavior, but also experiences the onset of permanent deformation. And we talked about how if I have some material and I stretch it out, if I stretch it out just a little bit, I sort of travel up this linear region of the stress strain curve, and then when I let go, it sort of goes back down to where it was before. So imagine I have one chunk of material, and I stretch it out just a little bit. I'm kind of exaggerating this right here. And then I let go. So I'm applying my forces, and then I let go. It can return to its original state as long as this force wasn't too big. And basically, when this occurs, we call it purely elastic. So what would that look like on the stress strain curve? I'm basically starting down here. Let's call this position 1, this is position 2, and this is position 3. So basically 1 is right here. I go up to some point 2 right here, and then when I let go, I go back down to my original position 1, which is sort of simultaneous with position 3. So as long as I don't put too much force on it, I stretch it out, it goes back to where it was before. And if you remember, we observed that not in pure tension, but in bending with the paperclip. Again, if I bend the paperclip just a little bit, it goes back to where it was before. So I'm doing this to various parts of this paperclip right here, this purely elastic deformation. But we don't, sometimes we take some material and we bend it too much, or stretch it too much, or crush it too much. We can basically have a situation where we bring something past its yield point, right? So if we remember, this point right here is what we call the yield stress, the stress that basically corresponds to this point right here. So if I take some material, so I started at point 1, I apply even more force, and then I let go. It contracts a little bit, but it doesn't go all the way back to where it was before. So we sort of have some permanent deformation left over. So basically there's some elastic recovery, but also some permanent deformation. So if I consider this 1, 2, and 3, this guy goes up. We take it past its yield point right here, and then the trajectory it follows is one that is parallel to this original. It's parallel to this original curve right here, and it sort of goes down. So this is now 0.3 for the red curve. So 0.2 is right, 1 is right here, 2 is right here, 3 is right here, and basically there was this permanent strain right here. So if we wanted to sort of do a little bit of color coding, this region right here, this permanent strain is what I would call, you know, this part of the deformation, and this pink part right here is basically the elastic part. So you know, I stretched out, the elastic part went down, but the green part, that green strain, is left over in the material right there. Now, well, so now I have this thing right here. You know, what basically happens? Well, it turns out that this material essentially gets a new stress strain curve. So basically this permanent deformation right here not only just is sort of left over in sort of a physical reshaping of the material right here, but this material behaves, this permanently stretched and then changed material, this gets new material properties. And what new material properties does it get? It basically gets a stress strain curve. It gets a new stress strain curve that is what is left of the original stress strain curve. So basically its new stress strain curve is, it turns out it's not precisely this, but for all intents and purposes, it's basically the leftover part of the original stress strain curve. So what does that mean? That basically means that we've essentially changed the material properties of this right here. So, you know, what is strain hardening? Well, when does it happen? It happens when we bring something past its yield stress, but not all the way to failure, right? So this happens when stress is greater than sigma yield, but strain is less than the strain to fracture. Right? We haven't taken it all the way out here. So these are the conditions in which strain hardening happens, and it basically results in permanent changes to the stress strain curve, where now this material right here essentially has a stress strain curve that looks just like the leftover part. Of this stress strain curve. And well, what's the key thing here? Well, the key thing here is now we have a new yield stress. So we could call this sigma yield new, right? Or sort of what the new yield stress rate is, right? It's essentially this material, after I've deformed it, it now has a different stress strain curve than what the original material was. And you know, it still has the same Young's modulus, right? The slope of the linear portion is the same, but now it has a new yield stress. So what's the key thing here? Well, in order to sort of compare what the new stress strain curve, you know, looks like compared to the old one, let's just sort of imagine that this new stress strain curve, I kind of cut and pasted it and sort of shifted it over to what, you know, to sort of what the same original axes were, or the same original origin. was, right? If we plotted stress versus strain, you know, the original curve looks like this. The new curve looks like this. They lie on top of each other for a little while, but we now have a higher yield stress, and sort of only this much strain between when the fracture is. So what are some key the key sort of changes? Well, we basically have a higher sigma yield, right? Sigma yield goes up, right? That's a key change that happens. But what are some other factors that change? We basically have a lowering strain to fracture. So take a moment now, pause and ponder. How is the toughness affected? So how is toughness affected by strain hardening? Well, the key thing here is, you know, your yield strength is increased, but this reduction of the strain to fracture, again, remember, toughness is the area under the curve. So if I were to think toughness, you know, the area under the light green curve is basically this, but the area under the dark green curve is much larger. It's the whole, you know, this whole region all the way out to here. So typically toughness is reduced. And a qualitative way of thinking about toughness being reduced is it basically makes materials more brittle. More brittle or less ductile. And you can imagine that has some serious implications for design, right? So, you know, if you're manufacturing if you're manufacturing bicycle helmets, right, which is something that you want to have a lot of toughness, so they don't break, you know, when they're, you know, subjected, so they don't break when they're subjected to impacts. You know, you want to make sure, like, no, you know, we want to make bicycle helmets out of very ductile plastics. We don't want to make bicycle helmets out of brittle glass. So, you know, yes, yes, our yield strength goes up, but this reduction in toughness is very problematic, and it's sort of and the main driver in this reduction of toughness is this lowering of the strain to fracture. That's essentially sort of what you get by having only this remaining part of the stress strain curve left over. So, you know, toughness is reduced. This is something we're usually sad about. But, you know, but there might be some circumstances where toughness isn't that important. A high yield stress is important. So this idea of strain hardening is basically, you know, hey, you know, we don't even need to get a new material at all. Just by strain hardening something, you can actually increase its yield stress. And as long as you keep that strain below the fracture, we can follow the Kelly Clarkson vibe, where what doesn't kill you makes you stronger. Something a little longer. Something a little. This is what she was talking about when she composed this song. I guarantee it. No, but I mean, it's real, right? As long as we didn't fracture the material, we actually increased its yield stress. You know, we decreased its toughness, we made it more brittle. Again, I don't know if Kelly Clarkson was getting at this philosophically as well, but the key thing here is it's harder. So our hardness increased, but our toughness decreased. So the stress strain curve, you know, the changes in the stress strain curve are accompanied here. It turns out that when we're considering this idea for strain hardening, this can basically be a local effect. So strain hardening can be local. So what does that mean? Well, let's do a little example here, a little demo where we have a paperclip, and I encourage you to pause the video now and actually go into your junk drawer or your desk or whatever and grab a paperclip. Take this paperclip and remember what its original shape is. Then take the paperclip and just holding one side, not holding it by the curved part, but just holding it kind of by the edges of the curved part. Bend the paperclip to try to straighten it out, and then try to bend it back the way it was before. So try to bend it to make it straight, and then try to bend it back the way it was before. And in doing so, you'll notice that I can't really bend the paperclip back in the same shape. Right? So strain hardening can be local. It's hard to bend the paperclip back to the original shape. Sorry, that says shape right there. And why? Well, you could imagine that some of the paperclip retains the original dark green curve, but other parts of the paperclip, in particular the ones that I deformed to try to straighten it out, retain the light green part of the paper, or obtain the light green part. So originally, basically, let's say the whole paperclip is dark green, and then I applied some bending, some forces to bend it, and what happened? Well, I took the paperclip, and in order to straighten out what was this curved section, I took this region here and I had to deform this, this region right here. So basically I had to deform and thus strain harden. I had to deform and thus strain harden this material right here. And then this part, this part right here, and I didn't really need to actually materially deform that. I moved it, but didn't really materially deform it. So what does that mean? Well, that means I've basically altered the mechanical properties of this region right here. And if I've altered the mechanical properties of this region right here, when I go to bend it back, this part is now stronger than its neighbors. And if this part is stronger than its neighbors, you can see now how this is kind of this sort of like goofy straightened out shape. So when I went to bend it back, this green part wants to stay straight. Yeah, I strain hardened it, and now it's stronger than its neighbors, and it wants to stay straight, so its neighbors actually deform when I try to bend it back in the original shape. So, what does it look like? This green part basically stays straight, and now sort of all of the deformation had to occur not in the straightened out green region, but in the parts next to it. So now the deformation in bending back happened here in the soft regions next to the strain hardened regions. So, so if you're designing, so for people who are designing, for example, like stents to be inflated inside of, someone's artery to prop to prop those arteries open, right? You might have seen them kind of have this like sort of like woven, right? They sort of have this like kind of woven design. When they're expanded, designers of stents need to be very careful about this strain hardening property, such that when you start to inflate the stent, the parts where you want the deformation to occur actually occur in those parts and not in other parts that that are sort of have this have a lower yield stress than the parts that started deforming initially. So stent designers consider this, and that's something we need to be very careful of. And it's also this idea of strain hardening being a local phenomenon isn't something that occurs just within paper clips and stents, but it can also occur in tensile tests of materials. So it also occurs during tensile tests of materials. And and the key thing here is it's of some materials. So what's the key thing here? Well, imagine I have a specimen that I want to do some tensile testing on. And and I'm gonna apply some forces, and I want to generate a stress strain curve of this material right here. Well, no material can sort of be perfect in its creation, in that there might be some regions, I've kind of exaggerated them here, but there might be some regions that might have a smaller cross-sectional area. Right? There might be some regions that have a smaller cross-sectional area, some regions that have a larger cross-sectional area, some regions that have a smaller. And again, we try to manufacture these specimens to be as perfect as possible. But again, they're real specimens. No specimen is perfect. So take a moment now, pause and ponder. Where will yield occur first? Let's say in A, B, or C. Well, hopefully you've had a chance to pause and ponder. Yield will occur first in region C, right? Region C has the smaller cross-sectional area compared to A and B, and the smaller the cross-sectional area, the higher the stress, right? So smaller cross-sectional area, higher stress. Next question, pause and ponder. After C experiences some permanent deformation, where will yield occur within the sample? So will it keep yielding in region C, or will region A or B yield? Take a moment now, pause and ponder. Well, hopefully you've had a chance to pause and ponder. It was actually kind of a trick question. We actually don't know. In general, it's material specific. And some materials it basically depends on whether, and to answer this question, we basically need to know, does the strain hardening effect outpace the reduction in cross-sectional area when strain occurs? So if you remember, right, you take something, you stretch it out, see if region C, stretches a bit, right? If region C stretches a little bit, one option is, we would know that the yield stress in region C gets harder, right? Sort of similar to the paperclip phenomenon right here, right? So region C would get its yield stress. Region C would get its yield stress increase, but as C stretches out a little bit, its area is reduced. Is further reduced. And basically which effect wins, the increase in yield strength or the further reduction in area, is something that for some materials the yield strength wins. And basically if yield strength wins, so if yield wins, then strain occurs elsewhere. Then strain is shifted elsewhere. For this it would probably be to region A, the sort of second narrowest region. But if area sort of wins, i.e. area gets smaller faster than sigma gets larger, then this sort of effect is exacerbated. So then the localization is exacerbated. Is exacerbated, or is localization continues. And you can see this localization effect in the plastic bags. So I take this plastic bag, I start stretching it, and you can see that basically this part started straining first. Its cross-sectional area is reduced. And, whoops, I strained it a little bit too fast. But basically, like, I started stretching it, and it's, it basically one area started necking down. It started getting smaller. And all of the strain, right, basically this stayed just about as thick as it did originally, and the strain kind of continued happening in this region. So the plastic bag is an example where the reduction in area outweighed the increase in the yield stress, and this phenomenon, this necking phenomenon, occurs. So to sort of tie things back to our thing here, what I'm talking about right here is basically this phenomenon called necking. And so in particular, it's this last case, right, where basically the localization of strain into one region, causes that material to sort of neck down. It was originally wide, and then it necked down into this narrow region where sort of all of the strain was focused. And and when you're designing things, sometimes necking is good, sometimes necking is bad. Usually the safer thing to happen would be to sort of have that strain be localized elsewhere. So usually necking is something that you don't want in things, because it can basically cause all of the strain to sort of be localized to one region. And then if you've localized all of that strain to that one region, you basically make that one region very brittle, and that can be problematic from a design perspective if you want to retain some ductility in the device that you're designing. So, thus concludes our discussion of strain hardening, and basically, in the Kelly Clarkson sort of way, if you take something past its yield point but you don't break it, what doesn't kill you makes you stronger. But the other implications on material properties are that you reduce its toughness, you make certain regions more brittle, and that can have some weird effects in terms of localizing strain and permanent deformation non-uniformly within your devices and tissues too. So now let's move on to this discussion of fatigue. So when I think about fatigue, this is a cautionary tale. Ye be warned that even if you keep something below its yield stress, it could still break. So even if you design a material or a device to be kept below the yield stress, if it's loaded multiple times, it can still break. If it's loaded and unloaded, it can still break. And the phenomenon of it still breaking even when being loaded and unloaded many times is called fatigue. So what does that mean? What implications does that have? Well, as engineers, like this should scare you, right? You should be, wait a second, I thought this yield was this safe limit here, right? If we go back, you're like, Lannon, you told me that if we stay on this linear region, right, if we go up and down and go up and down, we're still okay, right? We return back to the place where we were. It was purely elastic, right? It was totally safe, totally reversible. And the answer is like, well, actually not really. So on a macroscopic, from a macroscopic perspective, we return to where we originally were, but this phenomenon of fatigue occurs with an accumulation of damage at the micro level. And basically what happens is if you have some device, I'm going to use sort of tension as an example here, but if you stretch it out and then let it go back, and then stretch it out again, and then let it go back, and then stretch it out again, and then let it go back. It turns out that even if we try to make materials, there are usually small imperfections in our manufacturing process. And those small imperfections can lead to, for example, very, very small cracks in the materials we've created. So basically there could be small cracks that these cracks might even be so small that you can't see them. They might even be so small as to sort of just be a part of the roughness of the surface of a material. And basically what happens is every time you cycle, you stretch it out, you let it go, you stretch it out, you let it go, you basically cause increasing brittleness and strain hardening at the tip. So basically you cause, every time you open up that crack and let it go and open up that crack and let it go, there are sort of two phenomena that play a role right at the tip of the crack. There's stress concentration, which we talked about last lecture, right? If you remember, that stress sort of has to get steered around that crack and it kind of bunches up, leading to a local high intensity of stress. right at the tip of cracks. And there's also increasing brittleness due to strain hardening. At the tips of these cracks. And for some materials, basically you stress concentrate it, you brittle. Yes, you increase the yield strength here, but by reducing that brittleness so much, eventually that crack just keeps opening, where every time you open it, you sort of get that crack to propagate just a little farther and a little farther and a little farther across. And I'm kind of exaggerating it here, but basically that crack, that every time you open it up, every time you stretch it out, that crack just gets opened more and more. And then eventually it basically crosses the whole device, and you get a catastrophic failure. And you can imagine from a design perspective, from an engineering perspective, that's awful, right? We don't want that to happen, right? So basically, you're driving along in your car, let's say this is the shaft of your wheel, where basically every time that shaft turns around, it kind of goes from being bent one way to being bent the other, right? As that shaft turns around, like the top is in tension, the bottom is in compression, or vice versa. Basically every time it spins, it's like it sort of gets loaded and unloaded and loaded and unloaded and loaded and unloaded. It's kind of doing this, right? So like the axles in your car experience something like this every time your wheel takes a turn, and every time it does that, you accumulate a small amount of micro damage. And if there were any cracks, those cracks can just basically keep propagating with every little cycle. Now, granted, these are small, and we don't really notice them all the time, but but this phenomenon can basically occur. And this occurs that basically even though we kept the macroscopic stress below the safe limit, because there was stress concentration at the tips of the cracks and at the roughness, we still get a little bit of yield or a little bit of fracture every time we put it under a cycle. And eventually, once we've accumulated enough cycles, that crack can cross and ruin things for us. So you might need to consider, like, okay, here Landon's drawn a couple of cycles. Usually this phenomenon doesn't occur over 3 cycles, but rather many cycles. So usually this takes many cycles of being loaded and unloaded and loaded and unloaded to fail. So just to kind of give yourself an idea of, like, how many cycles something might need to survive, let's consider the case of a replacement heart valve. A replacement mechanical heart valve. Right, so there are a handful of different designs of heart valves, but one example of a heart valve is sort of this like cylindrical section, and there are basically these flaps, and these flaps can basically go from being in a closed state to kind of being in an open state. Again, forgive my ability to try to draw 3D here, but basically the flaps can kind of open, they sort of open like a pair of doors, or like a pair of butterfly wings or something like that. Every time the heart beats, they flap open to let the blood flow, and then they flap closed once the regurgitation is attempted. And so basically every time there's a heartbeat, you can imagine there's a stress cycle on the struts. There's a stress cycle on the struts that basically support those flaps, right? Those flaps are attempted to be pushed along with the blood flow, and then when they close, so basically with every heartbeat, the struts that support those flaps are stressed. So we basically get a stress cycle with every heartbeat. So, give her and it's good to have kind of a rough estimate of, how many cycles do we need this thing to survive in order to serve its bioengineering function. So, let's just make a couple of assumptions. Assume, and this will be worked into a pause and ponder question. So pause and ponder, let's say there's 100 beats per minute is our heart rate. And, let's say life expectancy of the human who has this heart valve, let's say they're anticipated to live to be 80 years old. So life expectancy is 80 years old. And let's say the typical heart valve patient is let's sort of divide our patients into two classes. One class of patients that are 70 years old, and another class of patients that are 40 years old. So take a moment now, pause and ponder how many cycles for this patient, and also how many cycles for this patient. So if they're 100 beats per minute and a cycle is every beat, this person needs to last, this one it needs to last 10 years, this one it needs to last 40 years. Or, what are the considerations? Well, if you consider, there are 10 years, right? So it's like 100 beats per minute times, let's do for the first one, 10 years times, I guess 60 minutes per hour times 24 hours per day times 365 days per year. Or, we could have done the rent thing and said 525,600 minutes. We could have done that as well, but or we could do this calculation. It turns out that the number of cycles for the 70-year-old would be about 5.2 times 10 to the 8th cycles, right? This valve needs to last 10 at least. What is this, like 52? No. This is millions, right? Millions of cycles. 520 million cycles. That's a lot. 520 million of anything is a lot. For 40 years old, it needs to last 40 years. Right? Yikes. That's an awful lot. And you can double check me on the math, but I think it ends up being something like 1.6 times 10 to the 9th cycles. So this has got to last 1 billion. So it's got to last greater than 1 billion cycles. Holy moly, right? It's got to last a while. And it turns out that this actually informs what type of valves they use for what type of patients. Typically, the mechanical valves are used for the older patients, where their life is a little bit morbid, but their life expectancy is less than the number of cycles that the mechanical valves are designed to withstand. But for younger patients, they oftentimes, instead of using these mechanical heart valves, the design implication here is they basically use porcine or bovine tissue. So they basically use like decellularized pig heart valves as a tissue engineered valve rather than a mechanical. So they usually use porcine tissue valves. And the rationale for these porcine tissue valves is that the tissue can potentially last a longer time. But the upside of this is, I guess, not these bileaflet valves, but other types of mechanical heart valves. Those can be inserted just with a catheter surgery, whereas the porcine valves require sort of open heart surgery. So basically, the porcine valves can last a lot more cycles, but you need to do open heart surgery on the patient. But open heart surgery is generally safer with younger patients than older ones. These older ones, can be done. These can be done via endoscope or via catheter installed. These can be installed via catheter, which is a less invasive surgery. So these ideas of fatigue inform clinical choices from our surgeons and from our cardiac surgeons, right? I know some people, and I know one person who was sort of closer to this younger age group, and she was given a porcine tissue valve, and I know another person in this sort of older group who was given a mechanical heart valve, and the design choice was based on this concept of fatigue. But how do engineers know? How do engineers know what a safe limit is, right? There are some number of cycles here. How did engineers know that this number of cycles would be too many, but this number of cycles would be okay? So how do engineers know or characterize the number of a sort of safe limit given an expected or desired number of cycles? Well, they typically do this via experiment. So basically what they do, you could imagine doing it with a tensile tester, or it turns out that it's actually a little bit easier to sort of do it in a rotating thing where you basically have a shaft with a weight hanging on it, and you rotate that shaft a whole bunch of times. And every time you rotate it, you basically go from one part sort of being in tension on the top to then being in compression on the bottom, and then when it rotates back to being in tension in the top and then being in the bottom. So you basically rotate a shaft a whole bunch of times with a weight hanging off it. And based on the rotation rate, so based on the amount of weight, and the amount of weight basically governs how much stress you're putting the surface of that material under, and the rotation rate basically governs how many cycles it lasts. And basically what you end up doing is creating plots, material specific plots, where you basically put a safe limit of stress as a function of the number of cycles before failure. And oftentimes the number of cycles before failure, like usually sort of for visualization and convenience, usually people express these on a log scale, and it might be something like 10 to the power 3, 10 to the power 6, maybe 10 to the power 9, right? So these are sort of the order of magnitudes of the typical cycles that people might test these under, and that's what we do here. Rather than writing out sigma, engineers were sort of a little bit lazy, and they just called it S. I guess S for stress instead of sigma for stress, and hence this is why we call it an SN curve. Right? So what we call here is an SN curve, where we basically have our material impose a certain number of stress and measure how many cycles it takes for it to fail, and then we essentially plot that as a point. So take a moment now, pause and ponder what you think the relationship between S and N might be. Does it go up? Does it go down? Does it remain constant? So pause and ponder. You know, what do you expect your SN curve to look like? Well, for the fewest number of cycles, we expect the safe limit to actually be the highest. And if we want our thing to last more cycles, we need to continually reduce and reduce and reduce that safe limit, right? If it needs to last 1 billion cycles, we better keep that stress at a lower level than if we accept it only lasting 1,000 cycles, right? So this is sort of like designing for a lifetime use of our materials. Take a moment now, pause and ponder what's special. What is this point right here? So I guess if we do 1, what is this point? Well, this point right here is basically how much stress it can take if we only want 1 cycle before failing, and I would consider this the yield stress, right? For most applications, basically we've considered it failed if the material experiences any permanent deformation at all. So if we only want it to last 1 cycle, our S is the yield stress, and if we want it to last more cycles, we're reduced from that yield stress. And it turns out that, you know, different materials have different yield stresses, but also different materials have different ways that these curves kind of shape out over a certain number of cycles. And it turns out that for steel, it looks something like this. Where you kind of get the sort of piecewise behavior of it, where basically your safe limit, you know, starts at the yield stress, it drops down and drops down and drops down until about 1 million cycles. And the interesting thing for steel is once it's lasted 1 million cycles, it'll last forever. We could contrast this to aluminum, where aluminum actually has usually a much lower yield stress than steel. And not only does that safe limit go down, but it actually sort of goes down and 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 down, and eventually basically approaches 0. So aluminum basically, you know, sort of asymptotes to 0, whereas steel plateaus and basically has something where, you know, something made of steel, if it lasts for 1 million cycles, it's also going to last for 1 billion or a quadrillion cycles as well. And it turns out for steel, we kind of call, I guess, this point right here, this sort of the stress where it plateaus, we call this the endurance limit. So basically, you know, and for steel, this happens around 10 to the 6 cycles. Different materials might have different stress, different proportions of its original yield stress, and different numbers of cycles where it lasts here. And some materials like aluminum have no plateau at all, where basically, you know, it just continuously asymptotes all the way down to 0. And this has particular design implications. For example, aluminum is what we make airplane wings out of. So we make airplane wings out of aluminum. And I don't know if you've ever taken off, but if you ever look out of the window as the plane's flying, particularly if there's turbulence, you see those wings flexing a little bit. And, you know, every time those wings flex and unflex, they're fatiguing. You know, so you might be like, hey, wait a second, like what? Like, why are we making airplane wings out of aluminum if, if eventually those airplane wings are going to break due to that, I don't mean to give you anxiety about flying. Those engineers have done careful considerations about how many times those airplane wings typically flex in a given flight, and again, the stress levels that those wings actually experience are much less than these well characterized curves. So airplane wings out of aluminum, it's still safe to fly because engineers designed stress to be basically below where this curve is, so below the S of the SN curve. So airplane wings don't need to last an infinite number of cycles. Airplane wings maybe only need to last 10 to the third or 10 to the sixth cycles, or something like that, before the parts are replaced or the airplane is entirely decommissioned. So, but some things out of steel, if you need something, so why do airplane designers make airplanes out of aluminum versus steel? Well, the strength to weight ratio for aluminum is a lot better than steel. So it turns out that even though we anticipate this decrease in performance with the number of cycles, it's still a better design choice to use aluminum than steel for airplane wings, even given the loss in sort of performance with the number of cycles that we expect. But for some applications, where maybe weight is a little bit less important and the number of cycles are a lot higher, than maybe even 1 billion, something like that, steel might be the best choice there. So, thus concludes our discussion of fatigue and how the endurance limit is a characteristic of some materials but not necessarily others, and how the safe limit for our design stress decreases with the number of cycles that we have there. So thanks again for watching, and good luck with your study of biomaterials.